Hello ladies and gentlemen, today we're going to start talking about another form of factoring. One you've seen before in IM2 and the other one you have not seen, but we're going to teach it to you today. And these type of forms of factoring are called special patterns. So once you get the pattern down, they're pretty simple to do. The hardest part of special pattern factoring is recognizing when to do it. So before we start, let's do some review. Okay, we're going to simplify this. Factor this guy from what you remember, and then factor this guy from last time, from the other factoring notes that we just took. Alright? Once you're done factoring, what I'd like you to do, go on Google Classroom, and in the comments, all I want you to do is tell me if you got it, kind of got it, or no clue. So go back to Google Classroom, write in the comments that you got number 1, got it, kind of got it, no clue. Number 2, got it, kind of got it, no clue. And then number 3, got it, kind of got it, no clue. Okay? If you have issues with putting comments on Google Classroom, come talk to me during class time. So let's go ahead and do this. I'm going to simplify factor and factor. Okay? Okay, hopefully you figured out how to do those. Let's move on to the next slide. Okay guys, what you will see here is the steps to special factoring. The most important part and the most difficult part is step 1. In order to use special factoring, you have to identify these type of patterns. And most students who have issues with special patterns is because they can't identify it. But once you get comfortable with identifying the types of polynomials we can use for special patterns, then the actual factoring part is pretty simple. So the first thing you're looking for in order to use special patterns is this. Special patterns only occur when you have 2 terms. Okay? So if you see 2 terms and they ask you to factor, one thing that should go off in your head is that maybe I should try to use one of the special patterns. Okay? In part B here, subtraction in between the terms. So you have a minus sign in between the terms. This is only used for perfect square special patterns. Okay? Like in example A down here. Notice they have only subtraction in between them. Any other type is perfect cubes. Okay? And this is part C. In perfect cubes, special patterns is you're going to have cubes or powers of 3. And the sign in between the numbers or variables does not matter. So again, these 3 steps here, step 1A, Step 1B and Step 1C are how you determine if you're going to use special patterns. So we'll get into examples and I'll show you how to use that. But what I want to do now is, before we get into Step 2 and 3, I want to show you what a problem might look like if you're using perfect squares. So if you look at the 2 examples I put down for perfect square special pattern, you'll notice it falls under this A, B, and C identifiers, things you're looking for. So we only have 2 terms. In the first example, we have 4x squared is 1 term, and then we have 9 is my second term. We also notice that there's subtraction between both examples. So subtraction is a must for perfect square special patterns. And last but not least, after factoring out the GCF, you should have, in this case, perfect squares. And if you recall, perfect squares are when you can square root each term evenly. So if I square root 4, it gives me an even number like 2 or a whole number. If I square root x squared, it gives me x. I can square root 9 and it will give me 3. Same thing here for this example. Two terms, subtraction, and every term is a perfect square. Now if you look at special pattern for perfect cubes, I gave you two examples here. So let's go through the list again. For perfect cubes, again, you only need two terms. So we have two terms here, two terms here. The sign in special cubes, it does not matter. So this does not need to be subtraction. It can be subtraction or addition. It doesn't matter. And the hardest part to recognize perfect cubes is after doing the GCF, you want to make sure the terms that you have left over are perfect cubes. So to make sure we're comfortable with what a perfect cube is, 27 is an example of a perfect cube because it is the result of 3 times 3 times 3. So we could get 27 by doing 3 times 3 times 3. That equals to 27. So 27's a perfect cube. X to the third is a perfect cube because it's x times x times x. So that's what a perfect cube is. It's the number that you get by multiplying the same thing 3 times. In this example, 8x to the third plus 1, this is a perfect cube because we have 2 times 2 times 2. That gives me 8. And then we also have x times x times x. That gives me x to the third. And then you also have 1 times 1 times 1. That gives me 1. So this example here also qualifies for perfect cubes. Okay? So to sum it up, in order to use special patterns, there's two types. There's perfect squares and there's perfect cubes. The hardest part, I believe, is once you recognize it, is this. Recognizing when to use. So you're always looking for two terms. Okay? When you're dealing with perfect squares, you only need subtraction. When you're dealing with perfect cubes, it doesn't matter if it's subtraction or addition. And then the last part is, after you did a GCF, if there was a GCF, in order to have perfect cubes, you have to have numbers that multiply to themselves 3 times to get me these terms here. For perfect squares, these are numbers that multiply to themselves twice to get me these terms here. For example, 2 times 2 gives me 4. Therefore, 4 is a perfect square. 3 times 3 gives me 9. Therefore, 9 is a perfect square. Okay, so once you get down identifying special patterns, we then kick into how do I actually factor. And this is where step 2 and 3 come into play. All right, let's do a couple of examples. We'll start with example A and go from there. So in example A, the first thing we want to do is see if we can recognize if this is a perfect square or a perfect cube. So the first thing we want to see is, do I have two terms? So two terms, it's a binomial. Check. The next thing I'm looking for is, do I have subtraction or addition? So you look here, it's subtraction. So this could possibly be perfect squares, but it also could be perfect cubes. So now, the next thing I want to check is, do I have perfect cubes or perfect squares? So this is where we look at the terms. So 27 cannot be a perfect square because there is nothing that multiplies to itself that gives you 27. And plus, the big hint here is that we have x to the third. When you have a power to the third, that's automatically a perfect cube. It cannot be a perfect square. So this is a perfect cube. So now we're going to go ahead and factor it using the perfect cube pattern. I also forgot to mention is that this term is a perfect cube, but we also got to check that if the second term is a perfect cube. And once we realize it's a perfect cube, we can then go ahead and do the perfect cube pattern. So to use the perfect cube factoring pattern, we first must find each individual cube root. So in other words, we're trying to figure out what multiplies to 27, what number that you can use that will multiply to 27, but you have to use the same number 3 times. So what number can I multiply to itself 3 times that will give me 27? And that number is going to be 3 times 3 times 3. So the cube root of 27 is 3. Okay? Same thing goes for x. What can we multiply to itself 3 times that will equal x to the third? That's going to be x times x times x. So the cube root of x to the third is x. So we are done with the first term. We're going to try to find the cube root of the second term. So what number multiplies to itself 3 times that will give you 64? And that number is 4 times 4 times 4. So the cube root of 64 is 4. Once we have the cube roots, the hard part is done. We have to just remember a specific pattern. Okay, so I'm going to write the pattern out. You could always rewind the video to see the pattern in mathematical form, but I'm actually going to write it out and show you how to factor this thing. So here's the cube root factoring pattern. I know it looks a little funky, but I'll explain it. So what this says is we have first set of parentheses, first, last, and then we have an S here. Then we have a second set of parentheses. Is going to be first to the second power. Here's an O, first times last. Then we have an AP, and then last to the second power. So what does all this mean? Quite simple. When you find your cube root of the first term, like we did here, we consider this our first. So I'm going to write this in. This is now our first term, which would make this cube root of our second term our last term. Okay, so now we know where first and last are, what numbers or variables they are. Now for the SOAP or SOAP, this is just telling you what signs you should use. So S stands for same. So that means it's going to be the same sign. You're going to put whatever sign here as your original problem. So in this case, it's going to be negative. The O stands for opposite of your original. So opposite sign. Let me make some room here. So I'm going to erase example D real quick. So O stands for opposite. So if this sign, your first sign is positive, this sign will be negative. If your first sign is negative, your second sign should be positive. So they switch. These should never be the same sign. Okay? And last but not least, the AP stands for your last sign. Your last sign is always positive. So AP. So I'm not going to write that all out, but always positive. So your last sign will always be a plus sign. So always positive for there. Okay? So saying that, let's go ahead and factor example A. So simply what we're going to do is take our first guy, in this case our first cube root, which is 3x, and he's going to go in this spot. So we have (3x), and then we go to the same sign. So the sign we have in our original problem is a negative. So I'm going to put a negative sign. And then our last cube root is, where's that? 4. Okay, so that's going to go here. And it's that simple. We're done with the first parentheses. Now we move on to the second parentheses. So we're going to take our first again. So we're taking 3x. And now we're going to raise it to the second power. So let's do that. So it's going to be 3x. And we put in parentheses because we're going to raise it to the second power. Now our sign is going to be opposite. So it was negative, so the opposite of that is positive. The next thing we're going to do is multiply our first guy times our last guy. So 3x times 4, if you put that here, that's going to give you 12x. And then our sign that we put is always positive, so we're going to put a plus sign. And then the last term we put is take your last guy and raise him to the second power, so 4 squared. So I'll put this in parentheses again. 4 squared. And now we're basically done factoring. The only thing we want to do now is we want to clean this math up. Okay, this is already ready to go. We're just going to clean this up. So 3x minus 4, nothing's happening there. This turns into, so 3x squared, that's actually going to be 9x squared plus 12x, and then we have 4 squared, that gives me positive 16, and this will be special patterns factoring cubes, or perfect cubes. Okay, example B is actually review from IM2, so I'm not going to explain it. I'm just going to do the work. And once I do example B, I want you to try C, E, and F. Okay? Remember, when you factor, the first thing you always want to try to do is GCF. Try to find a greatest common factor, factor that out, and then now after that, try to see if you can have a special pattern. So I'm just going to do the work for B. I'm not going to explain it. Hopefully you can follow that work. It is IM2 review. And after that, go ahead and try C, E, and F.